Okay, good morning, everyone. I hope you're well. Fair bit of housekeeping to do this morning before we get back to open challenges and the reality gap today. First of all, congratulations. Hopefully, most of you, if not all of you, have completed the 10th and final assignment. Well done. I know for some of you who we're not so sure about your coding abilities. This was a formidable task to complete over the last 10 weeks. So congratulations. That being said, I know not all of you have a perfectly functioning system at this point. I'm going to talk about the final project in a moment, and the final project is broken up into a series of weekly deliverables of your choosing rather than of my choosing. You will have a little bit of time this week to catch up on polishing up your system and making sure that all the bits and pieces are working correctly before you push on to the final project. So I'll talk about the final project in a moment, but before I do, other news from the only planet in the universe that we know of that is solely inhabited by robots. That planet is Mars. I was hoping to remind you today that Ingenuity, which is the helicopter due to take off from the surface of Mars, I was hoping to remind you that it's going to take off tomorrow, but it turns out that it is not going to be taking off tomorrow. Ingenuity is healthy, but it needs a flight software update. So they are madly writing, JPL or Jet Propulsion Lab is madly writing a software patch for Ingenuity, and they're uploading it and validating and uplinking it. And hopefully Ingenuity will be taking off from the surface of Mars next week. I have I've directed you to a couple of PyroSim patches that you have had to add to PyroSim over the last few weeks. I got one more patch for you this morning, which we'll talk about in a moment. At least I feel a little bit better knowing that I'm not the only software developer that requires the development of last-minute patches. It seems NASA and the Jet Propulsion Lab also do so. So hopefully sometime next week, we will get to witness the very first robot ever flown in the atmosphere of another planet. Should be very exciting. Okay, almost as exciting, the final project in this class. So I'm going to talk a fair bit about the final project now because I just want to make sure that we're all on the same page about what's expected for the final project. Obviously, I can't cover everything today, so please unmute yourself and interrupt me at any time. That's perfectly fine. I want to make the best use of our time this morning to make sure that you're all oriented and ready and excited to tackle the final project. So if anything is unclear, please type something into chat or just unmute yourself and ask your question. Okay, basic idea behind the final project is now that you've finished the 10th and final assignment, you are not at the end, but you're at the end of the beginning. We have implemented pretty much the simplest version of all the components that make up an evolutionary robotics experiment. You have the robot itself. It's not quite minimal, but it's pretty minimal. It's got a pretty minimal neural network. It's filled with sensor neurons and motor neurons, but we have no hidden neurons, no recurrent connections, no self connections, no bias neurons, no central pattern generator, all the other neural bits and pieces that we've talked about over the last few weeks. So a relatively simple robot body, a relatively simple robot brain. We have a simple optimization method, the parallel hill climber. It's extremely simple. It's just one step up from the hill climber, arguably the simplest search method. We have a relatively simple simulation. The robot exists in a pretty simple environment. It's an infinite flat plane with just one other object in the environment. So the way to think about the final project is you can take one or more of those components and make it more complex or enrich it in some way, and then ask the question, does that enrichment help at all? So for example, you could stick with the quadruped, you could stick with quadruped locomotion and replace the parallel hill climber with a different evolutionary algorithm and ask, does that different evolutionary algorithm make it easier to evolve quadrupedal locomotion than the parallel hill climber does. That's one example of a final project you might tackle. Some other advice I want to give at this 10,000 foot view is as you proceed, you're going to get stuck. It's inevitable. Some of you may be stuck already on the 10th assignment or maybe an earlier assignment. I'm guessing that this is probably the largest code base you've developed in any undergrad class at UVM so far. So big, in fact, that you may not remember where things are. Right. So as you start in on your final project and you're modifying the evolutionary algorithm or the neural network, most of the time you're going to be asking yourself, where do I need to go to add hidden neurons or to add the number, change the number of synapses that are sent to the neural network rather than just changing their weights. So I would counsel you to spend some time over the next few days just reviewing your code base. And the easiest way to do that is to remember that you have two code hierarchies now. You have search.py over here and simulate.py over here. And each of those two Python programs create objects or class instances. Those objects create other objects, and down and down and down you go. Search creates parallel hill climber. Parallel hill climber creates a population of solutions. And I don't know if we go further than solutions. I don't think so. On the simulate side, simulate calls the solution, creates a solution, a simulation object instance. Simulation creates robot. Robot creates a number of sensors and motors and so on and so forth. So just I would ask you to just start at the top and sort of read through or scan through those files. So again, you refresh this big picture view of all the code that you have so far. The other thing you're going to want to do as you're working on your final project, as you start to make changes, there's two different paths you can pursue. You can reach into the code, make a change, and run search.py and cross your fingers and hope that it doesn't crash. Or you can treat your code base as a complex machine, and like mechanics or surgeons, anybody that works on complex machines, they have the ability, the expertise to be able to break that machine open, to cut it up into pieces very carefully, and then put those pieces back together again. I would counsel you to follow the second path and resist the temptation to just make a change to your code, cross your fingers, and hope for the best. If it crashes, you won't know why it crashes. And if it doesn't crash and it looks like it's working, you won't know whether the change you made is having any effect, good or bad, on your code, right? So you don't want to proceed blindly because it's hard to make progress. That's like working on a complex machine, closing your eyes, making a little change, and hoping that you don't break the machine. Not a good way to proceed. Throughout the instructions, especially for the last few assignments, I've had you put exit statements in strategic places throughout the code base. So to stop search.py, to turn it off, and then use the files that are being written by search.py to diagnose or check that whatever change you made on the search.py side is showing up in the files. And then running simulation.py yourself at the command line or inside your IDE, watching simulate.py, watching it read in those files and simulate them, and then stopping. So I set up these two hierarchies on purpose to make it relatively easy for you to sort of cut them down the middle and diagnose or check each one individually. I would suggest you get very used to doing that in your final project. Whatever change you're considering making, make that change in the code, and then check the intermediate files, the files that are written out to disk, to make sure that change was made. Okay, that's sort of high-level strategic advice about the final project. Any questions, comments about anything before we dive into the nitty-gritty details? Going once, going twice. Okay. Okay, so you'll notice here this morning, as usual, you're being assigned some work to do, but it is no longer an assignment. It's a deliverable, which is due, as usual, next Monday at midnight. Okay, so what is this deliverable one? If you click on this link, it will take you to this Google Doc. This Google Doc will contain all of the information about your final project. So if you ever get confused and wondering what you're supposed to be doing for the final project, all the information should be in here. Okay, so today is Tuesday, April the 13th. We have a little bit more than a month together. Our final exam period is Monday, May 17th. There is no final exam in this course. You're going to be presenting your final project orally during the exam period. We'll talk about that in a moment. So what are you going to be doing over the next month? Well, over the next 3 weeks, right? I guess over the next 4 weeks, you're going to be delivering weekly reports or weekly deliverables demonstrating that you're making progress towards your final project. Each of them is worth 6%. I'll talk about these deliverables in a moment. You're going to be delivering one next Monday, the second one the Monday after that, the third one the Monday after that, and then the Monday after that is the second last day of classes. You will have nothing due on that day to give you a little bit of a breather, end the semester gracefully, and start to get ready and reorient yourself for the exam period. Okay. A week after that, the night before our final exam period, you're going to be submitting two things: a written report, which again I'll talk about in a moment, and you'll be submitting your oral presentation, which is going to be a YouTube video. So you're submitting a written report and a YouTube video. And then Monday morning, when your I'm going to play all the YouTube videos. When your YouTube video comes up, you will unmute yourself and talk over your YouTube video. Your YouTube video will be completely silent. Okay. That's not the 10,000-foot view, 5,000-foot view. Okay, so what exactly are you going to be doing in this final project? I realize that there are many of you in this course, and some of you are much more comfortable with your coding abilities than others. So I have tried to create two different ways to attack the final project: the sort of quote-unquote easy path and the quote-unquote hard path. I put both words in scare quotes because for those of you that are just starting to become comfortable with coding, the easy path is not so easy. And so there should be about the same level of difficulty for all of you. If you're not that comfortable with your coding abilities, I would suggest you follow the quote-unquote easy path. For those of you that feel you're pretty good coders and you want to try something ambitious or something of your own choosing in this over the next month or so, please follow the quote-unquote hard path. For the graduate students that are taking this course, I expect you to follow the hard path and to come up with a project of your own choosing. We can talk about that a little bit later. Okay, so what exactly is the easy and hard project? As I mentioned, some of you have different comfort levels when it comes to coding, so I've created these two paths. The easy path is to choose, you may choose to complete 3 one-week mini projects. So as you're going to see in a moment, I've described some sort of mini projects that should easily be completable with 1 week's worth of effort. So you'll be completing, if you take the easy path, you'll do 3 of these mini projects 1 week after the other. Okay. Or if you're going to follow the hard path, you can tackle 1 more challenging project that takes 3 weeks to do. So this will take us to the end of deliverable 3. I'll talk about what you'll be doing between deliverable 3 and the exam period in a moment. Okay, so why is the easy path easy? It's easy because if something goes wrong in one of the mini projects and you can't quite complete it, no problem. You can start fresh the next week with another one of the mini projects. You don't go too far into the woods and get completely lost. Okay, the hard path is more risky because you're biting off something that's more ambitious, but it's also probably going to be it's going to be higher reward because you'll have more room to explore your own ideas. As you'll see in a moment, I give you less details about how to complete those projects, and so it'll end up simply just being more intellectually rewarding for you. Okay. No student is going to be penalized for choosing the quote-unquote easy path because, as I mentioned, if you're not that comfortable with coding, the easy path is not necessarily going to be easy. Okay. All right, so there are pointers in this document to yet another Reddit page, and this Reddit page is the final project. So this is the final module on the Reddit side of the course. And in this module, there are listed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different possible projects. And you'll notice each of these 16 projects has an easy or hard tag associated with it. So the easy are the mini projects that are completable in 1 week, no problem. The hard ones, as far as I can estimate, for most of you, it'll take you it'll take you about 3 weeks to do. Okay. So if you choose the easy path, you're going to be please choose from any of the easy options from here. If you choose the hard path, you can choose the hard paths from the same page, or you may formulate your own. If you have your own idea that you want to try and tackle, please do come and see me during office hours or email me a very short email, 3 sentences maximum, describing your idea. And I will just give you some feedback on whether it's feasible in PyroSim. I don't know how good a coder you are or not, so I cannot comment to whether you can complete it or not. All I can do is tell you whether it's feasible, whether it's something that can be made in PyroSim. Up till now, you've only been using one type of sensors, the touch sensors. You can, in theory, create distance sensors and light sensors and proprioceptive sensors. Some of those sensor types are feasible in PyroSim, some are not yet feasible in PyroSim, for example. Just let me know what you're thinking about and we can work it out. I'll just pause for a moment. Any questions, comments? Feel free to unmute yourself if you have a question.
For the grad students, can they do like one of the hard projects that you give them, or do we just have to come up with our own?
Yeah, if you're a grad student, or you just choose the hard path, you don't have to come up with something on your own. You can come up with your own idea or follow one of the hard projects. No problem.
Okay, thanks.
Yep, good question, Hannah. Anyone else? No? Okay, so deliverable 1, let's talk about that. So the reason that you're handing in something every week is sort of just to keep you on track. In previous years, I had you submit nothing for a month and then present your work during the exam period. I was a student once. I know what happens if the instructor gives you a month to do something. It's unlikely you're going to be starting the next day on that project if you got a month to do it. So the deliverables are there for you to help you put in a little bit of effort every week on the final project. So you're not staying up all night during the exam period to try and finish a final project when you have other exams and other projects to do. Okay, so this week and next week and the following week, the deliverables may feel like a pain in the butt, but they're there for a very good reason. Okay, so what are you submitting a week from now? If you choose one of the easy projects, you're going to be submitting one video demonstrating that you've achieved that project. So you got lots of experience now doing this. It's up to you, however, now what you show in the video. But as you know by now, we're going to be looking in that video and you should make it very clear that we can see that you successfully completed whatever that project is. And I'll go through this list quickly. I'll go through this list quickly in a moment, in a few minutes. Okay. Same thing as usual, like for the assignments, when you create a video demonstrating your deliverable 1, upload the video to YouTube, get the YouTube URL, drop it into a Reddit post, submit the Reddit post, and then copy and paste the Reddit URL into Blackboard. I know, again, it's a pain to go from YouTube to Reddit to Blackboard, but the reason that we have this pit stop in Reddit is, again, so that your fellow students who are taking this course purely online can keep up with you. And also, obviously, you can look at the other Reddit posts coming in from the other students to see what other people are working on, to get a sense of what's easy, what's hard. You might get some inspiration for ideas for the following week. That's perfectly fine. In the final project, it's expected that you're working on your own. It's not a group project, but it is a group project in the sense from the Reddit point of view where you can definitely look at the work being done by your fellow students and hopefully draw inspiration and get a sense for what works and what doesn't work. That's perfectly fine. Okay, so next Monday, you're submitting one video demonstrating that you've achieved one of the mini projects. When you submit it, we want you to type a couple sentences into the Blackboard submission because Amanda, the TA, and we are not going to remember what everybody's working on every week. So please write a very short summary, just one sentence of what your project is, and maximum 3 sentences of what we're supposed to see in the video. Amanda and I are going to have to grade 60 of these submissions every week, so please don't write a novel. Keep this very concise and precise. Let us know what you're doing, what we should see in the video, then we'll go watch the video, and if we see what you told us we'd see and it sufficiently demonstrates that you successfully completed the mini project, you're all good. Okay. If you choose the hard project, then obviously in this first week, you should only be 1/3 of the way through a hard project because a hard project takes about 3 weeks to do. Okay, so you're going to be submitting a video again, but that video should be demonstrating that you're about 1/3 of the way through completing that project. What is 1/3 of the way through? I don't know. Amanda, the TA, doesn't know. You know. You tell us what that third increment of progress is and how it's demonstrated in the video. So again, when you submit the video, make sure to describe in a few sentences inside the Blackboard submission, first of all, what your project is, so we don't have to go look it up and remember, and let us know what we should see in the video. Again, keep this very brief. What you plan for next week. So here is me demonstrating to you. I'm 1/3 of the way through. This coming week, I plan to add X, Y, and Z. Okay, and finally, and then the following week, in the 3rd week, I'm going to add the cherry on top, and the cherry is this, and that will complete the project. Please keep this to just 3 or 4 sentences if you can. Okay, so what does this mean to demonstrate progress towards a final project but not completion? Here's an example of what this might look like. One of the hard projects you'll see in the list in a moment is to evolve a robot that avoids objects in its environment. Okay, that's pretty vague. How do you go about doing that? So here's a hypothetical student who has taken this project. They've thought about this project a little bit, and they've broken it down into the following 3 pieces. And this is them reporting in Blackboard what those 3 pieces are when they submit the first third in deliverable 1, second third in deliverable 2, and the third and final piece in deliverable 3. So in deliverable 1, they tell us that I've modified the parallel hill climber side of my code base so that the same solution is written out twice, but 2 different worlds are written out. So in other words, this student has decided to take solution.py and send out the neural network twice, and send out the world.sdf file twice. In the first time world.sdf is written out, the student in these two different world files, they create two different worlds. The first time, the block is placed directly in front of the robot. In the second world, the block is placed directly behind the robot. You might already start to figure out what the student's strategy is. If you want to evolve a robot that avoids objects in its environment, it might make sense to evaluate every robot, or from the point of view of the code base, to write out every solution multiple times, to expose that solution or that robot to different environments and to see how well it does at avoiding objects on average. This is a common theme in several of the hard projects. Okay, so they're just demonstrating that they can write out these files and play them back in simulate.py in the first week. In the second week, the student says, I modified the parallel hill climber so that now it reads in two fitness files for each solution. So solution writes out two world files and starts up two simulations. How does the robot do in world A, and how does the same robot do in world B? And the parallel hill climber is now reading in how well the robot did in those two in those two environments. And it reads in those two fitness values and combines them into a single fitness value for that solution. We'll assume in this example that the video shows search.py stopping after it reads in both fitness files. The video ends by showing the file directory with the two fitness files sitting in it. So remember that search.py reads in a fitness file, gets the fitness value out of that file, and then deletes that file. The student in this deliverable has chosen to stop search.py just after it's read in these two fitness values, but just before it's digested and deleted those two files. Yeah. So this is the idea of cutting your code into two and demonstrating the two halves of your code working. In deliverable 1, it spits out two worlds. Deliverable 2, it simulates both worlds, spits out two fitness values that are read in. In the third and final deliverable, the student is demonstrating completion of this project. The student says, I worked on the fitness function to reward positive Y movement in the first case. So when the object is placed directly in front of the robot moves backwards. And when the object is placed directly behind the robot moves forwards. I think this should actually be minus Y and plus Y. Doesn't matter for our purposes, this is just a hypothetical. But it's demonstrating that in one case we want to reward movement in one direction, away from the block, and in the other case we want to reward movement in the opposite direction, again away from the block. The student goes on to say, as you can see in the video, this led to the evolution of a robot that moves backward when it hits an object placed directly in front of it, and moves forward when it hits an object placed directly behind it. Okay, you can read this more at your leisure. Remember that our robot is blind at this point. It cannot see, it has no eye, it has no camera, it has no infrared sensor, it has no distance sensors, it can't see anything. So if we want it to respond to objects in its environment, the robot is going to have to touch those objects, right? That's why the object is placed directly in front of the robot and directly behind the robot in this project. So this student has gone from this, thinking about how do we evolve a robot to avoid objects in its environment, to this idea, and they've broken that idea into these three pieces. For those of you tackling the hard project starting this week, that's the main effort you're going to be doing, thinking about the project and thinking about how to carve it into three pieces. Any questions about that before we push on? Okay. Okay, so deliverable 2, what are you submitting 2 weeks from now? If you're following the quote-unquote easy track, that will mean that you will have completed one of the 1-week projects from the previous week. So simply pick another mini project and complete it. The order in which you do the easy projects listed on the Reddit final project page doesn't really matter. There's 1, 2, 3, 4, 5. There's 5 different easy projects to pick from. You can do them in any order. If you want, some of them build on top of the other ones. So you can either add it to what you did last week, or you can start again. Or you can start again by creating a new Git branch off of your quadruped assignment. So your current branch of your code base is called quadruped. So you can create a new branch called Project 1 in the first week. When you're done with Project 1, you can go back to your quadruped branch and create a new branch called Project 2, which is sort of going back and starting again. Or you can build on top of the mini project from the week before by creating a branch off of your most recent branch, and like you've been doing through the 10 assignments. So, for example, if you evolved a jumping quadruped last week rather than a walking quadruped, in the second week you might evolve pronking. So pronking is this beautiful gait exhibited by certain animals, which is jumping while moving forward. There's a very clear stance phase in which all 4 or 6 legs are on the ground, and a flight phase in which all legs are off the ground. Given that, you can see how doing jumping 1 week and then pronking the next week, it would make sense to build pronking on top of your project from the previous week. Okay. On the other hand, if you want to start fresh, if you did jumping the previous week, you can discard jumping and instead tackle another mini project in which you get your quadruped to move through a debris field of cubes. You can sprinkle cubes in front of the robot by altering world.sdf and evolve your robot to plow through those cubes. That behavior doesn't have much to do with jumping. Makes sense to start again. Doesn't matter to us. Just make sure you tell us what you're doing when you submit your deliverable 2 in Blackboard. If you're doing one of the 3-week projects in deliverable 2, remind us in your Blackboard submission of what you did from the previous week, describe your progress this week, and upload 1 video showing that you're now 2/3 of the way to completion. Pretty straightforward. Okay, in your 3rd and final weekly deliverable, if you're doing the easy track, do a 3rd mini project, build on what you did before, or start fresh, doesn't matter to us. If you're doing the 3-week project, again, remind us in your Blackboard submission of what you did last week, describe your progress this week, and upload 1 video showing you have completed the project. Please keep in mind that we are grading 60 of these every week, so please keep your text to a minimum, and please do not submit 5 or 10-minute long videos. Keep them to about the length that you've been submitting throughout the assignments. You should be able to communicate to us your progress in a video that is 60 seconds or less. We very much appreciate it. Any questions about the deliverables? No? Okay, I'm just going to scroll to the top here for a moment. Once you've submitted your 3rd and final deliverable, you have 2 weeks until you're presenting your final project. What are you doing through those 2 weeks? Well, at the end, by May 3rd, you'll have 1 or more projects implemented. Your robot will now be jumping rather than walking, or avoiding objects, or pronking, or doing something else. What we would like you to do is what's called an A/B test. And I haven't written this up yet. I haven't described the written report and the oral presentation where you'll be demonstrating this A/B test I will fill this out in the coming weeks, and we'll come back and talk about this. But I just wanted to give you a heads up about where you're going. What is an A/B test? Well, an A/B test is a common idea in engineering where you have version A of some system, you have version B of that system, and you compare them head to head. Which does a better job? A/B testing is very common in web development. You create two slightly different versions of a website. When people arrive at your website, you randomly show them version A or version B, and you record how long they stay on either version of your website. If people stay longer on A, then A is better. If people stay on B, B is better. What does an A/B test mean in this course? You're going to be making changes to your code, and you can ask the question, what changes make it easier or harder for evolution to proceed? So if you create a jumping robot, you can make some slight changes to the evolutionary algorithm, like the mutation rate, how often things are mutated or how much they're mutated. And that can be version B. So what you did during the deliverables becomes version A. You're able to evolve a jumping robot. You now try and improve your evolutionary algorithm, and does that version B produce higher jumping or better jumping? You're comparing A or B. One of the hard projects is to increase the brain of the robot, to add in hidden neurons and recurrent connections and so on, and basically make your robot brainier. You can again do an A/B test and demonstrate that to us on the 17th, where version A is evolving quadrupedal locomotion with the neural network from assignment 10. Version B is also evolve quadrupedal locomotion, but evolve it with the bigger brain, more neurons, more synapses. Does the parallel hill climber have an easier job evolving locomotion with the bigger brain than the original brain or not? A and B. That's what an A/B test is. That's what you're going to be showing us on the 17th. Okay, we'll talk more about A and B testing in a couple weeks, but I just wanted to give you a heads up. The oral project in particular, we have a little less than 3 hours. We have 60 of you, so you're not going to be speaking for very long. Your oral presentation is going to last 2 or 3 minutes. I'm not sure exactly how long yet. You're going to be submitting a silent 2 or 3 minute YouTube video. We're going to create a playlist, a 2 hour and 45 minute YouTube playlist with 60 2 or 3 minute YouTube videos in it. I will play that YouTube playlist starting at 7:30 a.m. on Monday, May 17th. I will share my screen, so we'll all be watching the YouTube playlist together. When you see your video come up, you will unmute yourself and narrate the video for us. That's how you'll be presenting your project orally. Okay. That's the final project. Any questions or comments? Again, feel free to unmute yourself and ask your question. Okay, as mentioned, there are links in this document to back to Reddit, and I've listed here all of the final project ideas. I'm not going to read through all of them. There's a lot of them, but I want to just touch on a few of them. I want to start by talking about housekeeping at the beginning. There's a couple of things you might want to change to your code now before diving in. These are the code patches that I mentioned. NASA's not the only one that supplies last-minute code patches. Here's a couple of last-minute code patches that should be able to help you before you get started. There's an optional one here. And then, as always, you'll start by creating a final project branch from your quadruped branch. Okay. Very briefly, just going through these projects, up, and away. This is the jumping project. Can you start to evolve a robot that jumps? This is a more difficult version of the jumping project. It turns out that getting something to jump is not that easy, but this easy project is a step towards jumping. I want everyone, when you start in on your final project, I want you to please read this document from top to bottom. I know you're not implementing every single project here, but I want you to get a sense of what's possible. By reading through, you get a sense of what's feasible, and you might get some ideas from some of the project descriptions that are helpful in other projects. So please read this in its entirety. It's not very long. 67 steps, not as long as some of the other projects. Okay, up and away, trying to do jumping, floating on air, actually achieving jumping. Stretch those legs, get the robot to sit on the ground and instead raise its legs as high as it can, kind of the inverse of jumping. Brainiac, the Brainiac project. So this is the one where you add in hidden neurons and recurrent synapses and self synapses, so improving the brain of your robot. Daddy Longlegs, this is an easy project in which you can evolve not just aspects of the robot's brain, but also aspects of the robot's body, which is to evolve the length of the quadruped's legs. Bodybuilding is a hard version of this project. This is not evolving length of the legs, but adding, moving, and deleting legs. So, well, you can read through this at your leisure. So instead of placing 4 legs radially around the robot's body, can you create a constant in the constants file where if that value is set to 5, it will place 5 legs equally spaced around the robot's torso. If you change that constant to 6, it'll place 6 legs evenly rotated around the robot's body. This is actually known as procedurally generated content. So this is turning your quadruped into procedurally generated content. This is an idea that comes from computer graphics. If there's any gamers out there, No Man's Sky, a very popular game, uses this idea of procedurally generated content. It's very popular in the computer games industry. For those of you that have ever wanted to give that a try, check out the bodybuilding project. Okay, the Many Worlds project. This is the one that I mentioned in the hypothetical project before. For each solution, you're going to evaluate that solution in n different simulated worlds. In order to do so, you need to write out different world.stf files. Okay. Can you get the robot to exhibit fear of the block? Walk away from the block once the robot comes in contact with it. Here's pronking, as I mentioned before. So building on top of the jumping mini project, you can do pronking. I don't know if I would count this as a hard one. I might reclassify this one as an easy one. We'll see. Project Runway. Modify world.stf to turn that block in the robot's environment into a tall but long platform. Drop the robot on top of the platform or the runway so that the robot has to evolve the ability to walk as straight as possible. If it doesn't walk straight, it falls off the runway and gets low fitness. Full steam ahead. Strew a bunch of blocks in front of the robot and evolve it to avoid those objects. Turns out that you don't actually have to alter the fitness function to select for object avoidance. Hitting the objects will simply slow the robot down. So the parallel hill climber, if you do this right, should evolve a way of moving that gets the quadruped to avoid hitting blocks. Walking and chewing gum at the same time. We've seen this already in many evolutionary robotics experiments. You can alter the fitness function to be A times B times C, where each component of the fitness function represents some different desirable property of the robot. You usually want A and B and C and D and E and F, if you add them, to be values, positive values, so that if A equals 0, meaning the robot does not do very well at A, but gets non-zero values for B and C, fitness is still equal to 0. 0 times a non-zero times a non-zero value is 0. So multiplying the terms together says the robot has to exhibit at least minimal competency in A and B and C. It has to be able to walk a bit and chew gum a little bit. Chewing gum is obviously tongue-in-cheek here for the robot. But here's an example of two different behaviors that you could reward for simultaneously. Move forward as fast as possible while also maximizing its height. So walk on your tiptoes. This is a step towards something we're actually going to talk about in a few weeks' time. We haven't got there yet, called multi-objective optimization. If we treat A, B, and C as objectives, we might want to simultaneously optimize or evolve those objectives together. This is a very simple way to do multi-objective optimization. We'll talk about more complex ways to do this later. Standing on your own 2 feet. Some of you have probably seen the Boston Dynamics Atlas robot doing its thing and dancing and jumping and doing all sorts of things. Can you create maybe not a detailed model of the Atlas robot in PyroSim, but a simplified biped, and evolve that biped to move? It's a tricky thing to do because evolving a biped to move forward is easy. The robot falls forward and then shuffles along the ground. Getting a robot to move forward while maintaining an upright stance, more difficult. That's why this is a hard project. Remember when we talked about legged locomotion, there were 4 different features of movement that evolution needs to reconcile or trade one off against the other. 2 of them were displacement, actually moving forward, and stability. In the case of a biped, that means staying upright. Okay. The Sit Good Dog project is also difficult. It requires considerable change to the quadruped to turn it from the quadruped into Boston Dynamics Spot Mini. Getting it to actually open a door while being hit by a hockey stick, maybe that's a little bit too difficult, but trying to create something that has legs and an arm could be an interesting project. Okay, an evolution revolution. As I mentioned, you might want to replace the parallel hill climber with a different evolutionary algorithm. Some of you may have taken the evolutionary computation course already. Some of you may be planning to take it in the fall. There are many, many different kinds of evolutionary algorithms. In my lab, we tend to use the AFPO algorithm, Age Fitness Pareto Optimization. There's a link to the research paper that describes AFPO. It's a pretty short paper, leaves out a lot of details. For those of you that want to attempt this project, send me an email or come and see me during office hours, and I can give you some help getting set up on AFPO. Strength in numbers. You can actually create a swarm of robots in PyroSim. It's not too hard, but it is still a hard project. Like the Many Worlds project, where we write out multiple world.sdf files, if we want to create a swarm, you can write out multiple body files and then alter simulate.py's code hierarchy to read in all of those body files and simulate them simultaneously. It's not that difficult to do. Could be an interesting project. Okay, those are all the different projects I could think up. There's many, many more you can do, but I think these should give you a sense of sort of what's possible. And again, if you choose the hard track, you can come up with your own projects, but I would suggest you read through the hard projects in a little more detail first to get a sense of what's possible. Any questions about any of that? I realize that's a lot of information. I'm recording today's lecture. You can go and replay it on YouTube to listen again. Please make sure you understand what's expected of you for the final project before you dive in. All good? Okay, I think we finished up the Golem project last time, but just very briefly. We were talking about the Golem project reported in 2000, over 20 years ago now. It was basically the public's first exposure to 3D printers, and in this case, they were being used to print the plastic shells of robots that had been evolved in a simulator, in a physics engine. I ended last time by showing you the Fab at Home project. This was an attempt to make 3D printers, make a 3D printing kit that you could buy and make at home. Part of the Fab at Home idea was if you could make it at home, you might actually get your homemade 3D printer to print out some of its own parts. That was even more the focus of the Reprap project here. I'm a little behind on where I wanted us to be at this point in the year, so I'm not going to play this video. It's pretty. Oh, it's only 2 minutes long. I guess let's play
a machine that could turn your desktop into a factory. I'm here at the University of Bath to see a machine.
I guess we're not going to play it. The audio doesn't seem to be very good on this video. I don't know how that's possible. Anyways, I can talk you through the Reprap project. This was a project that was carried out in the UK at about the same time the Fab at Home was being carried out at Cornell in the US. The focus here was to create a 3D printing machine, and the quality of that 3D printer was the percentage of its own parts that it could print. A 3D printer that only printed half of its own parts, and you had to buy the other half from Amazon, which was difficult to do back in 2000, but you get the idea, wasn't as good as a 3D printer that could print 90% of its own parts, and you only had to buy and install the other 10%. It's interesting to think, and no one's done this yet, but I'm sure it'll eventually be done, is to connect an evolutionary algorithm to the design of a 3D printer. So instead of evolving simulated robots, could you evolve populations of different simulated 3D printers where the fitness of any one 3D printer could be the percentage of its own parts that it prints? What other aspects of 3D printers might you be able to evolve if you were able to evolve 3D printers in simulation? Printing as many of your own parts as possible is just one aspect of a 3D printer's performance that we might try and optimize. What are some other aspects of a 3D printer's performance that you might want to optimize by including that feature in the fitness function? If you have an idea, go ahead and type it into chat. Or go ahead and unmute yourself and offer an idea. That's fine too. Alex says you could optimize the size of the printed objects. So we could evolve a 3D printer that prints most or all of its own parts, but the constructed child printer is 10% smaller than the parent printer. It's a great idea. Obviously, the speed at which it completes projects or prints its own parts are pretty important. 3D printing has come a long way in 21 years. We'll talk more about 3D printers in a few weeks, but it would be interesting to try and automate the design of 3D printers using something like an evolutionary algorithm. Nobody's tackled that yet. It's an interesting idea, I think. Okay, so that's the Golem project, and remember that the Golem project is the second attempt we've seen to address this open challenge in evolutionary robotics, which is crossing the reality gap. How do we get things that we've evolved in simulation to reality? One idea, the first idea, was simply noisify the simulation to make it more robust to changes, like, for example, transferring from simulation to reality. The Golem project says, why don't we just evolve lots of things in simulation and rapidly and cheaply and automatically manufacture them in reality. If only 1% of the things evolution comes up with transfer to reality, if we do that 100 times, we'll get something that crosses the reality gap. We're going to look at a third answer to crossing the reality gap now, which has become known as the Resilient Machines Project. This was a project carried out. By myself. I worked at Cornell back in 2006. At that time, NASA provided a grant to Cornell University that I worked on. At that time, NASA was interested in what they call methods of last resort. So if NASA sends a rover to another planet and that rover comes in a little bit too hot, it hits the surface at a faster velocity than was expected, and a wheel breaks off, or a leg breaks off, or a propeller breaks off, it could be potentially game over for a multi-million dollar, possibly billion-dollar project that's absorbed millions or billions of taxpayer dollars. It's taken 10, 20 years to design, manufacture, launch, and get the rover to that other planetary body. There is a lot riding on that one rover. If something really bad goes wrong, is there a method of last resort? Is there a way to get that robot to recover? This is separate now from the simulation to reality, the reality gap problem. I'm just giving you sort of the backstory for how this project came about. This project helps with the reality gap problem, as we'll see in a moment. So when I was hired at Cornell, I came up with the idea of a method of last resort, which is if a robot becomes severely damaged on another planet, can it move carefully, because it's damaged, can it move carefully to figure out what has occurred? Can it then diagnose the problem? Can it run a simulation on board? Can it run a physics engine on board where it evolves a description of the damage? So up till now, we've been trying to evolve solutions to a problem, which is locomotion. Imagine we're trying to evolve solutions to a different problem, which is evolve a description or a diagnosis of your current experience. Something has gone wrong, severely wrong, but the rover may not quite know what it is. A wheel or a leg may have broken off, but depending on how the rover lands, and maybe its camera is half buried in the sand, JPL back on Earth can't remotely diagnose what the problem is. Nobody knows what the problem is except that something really bad has happened. The robot may be able to evolve an understanding of what happened. I'm going to talk about that in a moment. Once it evolves the ability, once it diagnoses what the problem is, can it then run a second evolutionary algorithm to evolve a compensating neural network? Can it evolve a different way to move given the diagnosis? So imagine the physical rover lands on Mars and one of the wheels breaks off. The rover runs an evolutionary algorithm on board using a physics engine and diagnoses the problem. The only way to explain how I'm moving is that I lost my front left wheel. So the robot now knows that it's missing its front left wheel. It now runs a second evolutionary algorithm that searches for a neural network that allows it to move around with just 3 wheels rather than 4. That's the Resilient Machines Project. I'm going to talk about it in more detail in a moment. I'm going to skip this slide. So how did we test this idea? Well, we built this robot that you see here. Here's the robot moving in its intact state. This is just a summary of the project. I'm going to go into each of these 3 stages in a moment. We then simulated a catastrophic failure. You'll notice that there's a little piece missing from the front part of the robot. We've mechanically separated the front lower leg of the quadruped. The lower leg is actually lying over here. It's still electrically connected to the robot, so the robot can send commands to the motor controlling its front lower leg, but it has no impact on the robot's movement. Here you can see the damage a little more clearly. It turns out that this way of walking works when the robot has 4 intact legs, but this way of walking does not work when the robot only has 3.5 legs. So it's going to have to evolve a compensating neural network. It's going to have to evolve a different way to move. And in this tabletop experiment, it will not work. Not the most elegant way of moving. It moves along the surface of the table slower than it did before, but it's still carrying on with its mission. Its mission, in this case, is just to move from the left side of the table to the right side of the table. Couple details to notice from these videos. You'll notice the construction of this quadruped. It is not a coincidence that you just finished building a quadruped that has more or less this shape. We've used this particular body plan in our research for many years. Okay. Just a little anecdote about this story. It took us a long time. It took us 3 years of a lot of blood, sweat, and tears to get this project to work, to get to the point where the robot on its own could figure out what the problem is and evolve a description of what's gone wrong and evolve a compensating way of movement. It was about 3 in the morning one night in the lab when we finally got the damaged robot got itself to start walking again. Myself and a couple of the other members of the research team, we went absolutely crazy. We were super excited. We were screaming and yelling. There was an undergraduate student sitting at a bench in another part of the lab that had absolutely nothing to do with this project. He turned around and couldn't understand why we were all excited about this seemingly inefficient way to move. But he looked at this thing and said, "Dude, that's the evil starfish." So for better for worse, the Resilient Machines project and the robot that we used for this project has become known as the evil starfish. I'll probably refer to it as the starfish as we keep going. Okay, so what does this have to do with the reality gap problem? Well, let's sort of take stock of where we are in the course in our discussion of evolutionary robotics. There's arguably 3 different ways to approach evolutionary robotics. As we saw in the early history of evolutionary robotics, back in the early 90s, there were no physics engines. So they basically evolved controllers on the little hockey puck robot, the Kepra robot. They did evolution directly on the physical robot, but it took days and days and days of experimentation to do so. Because as you now know, the parallel hill climber and other evolutionary algorithms require hundreds or thousands of evaluations in order to start to get useful behavior. Takes time. This also inflicts a lot of wear and tear on the physical machine. You can wear out the robot, you can flat out its battery before evolution finishes. So starting in the late 90s into the very early 2000s, the emergence of physics engines in the computer games industry, those physics engines started to trickle into robotics research, and which has now become the most popular paradigm, which is create a simulation of the robot and do all the evolution inside the simulation before transferring an evolved controller. Or in the Golem Project, which we just saw, transfer the physical body to reality. What's the drawback of sim to real? It requires a human to handcraft a simulator. You now all have firsthand experience of how much effort it takes to construct a virtual world, a virtual robot, virtual sensors, virtual motors, and so on. A lot of human effort goes into the behind the scenes. The second problem is our focus of discussion these weeks, which is the reality gap problem. Okay. There's a third approach which we actually haven't talked about in this course, which is to try and come up with manually design an OK controller for a robot, and then allow evolution directly on the physical device, on the physical robot, to tune or improve that controller. It's okay, but it's, again, an approach that's not used very much because it requires a lot of human effort. You need a human to handcraft an original controller for the robot. If you think about your quadruped, you could probably write down a controller that works. If the touch sensor in the front lower leg comes into contact with the ground, pull or contract the knee joint. If the back lower leg comes into contact with the ground, push. If you pull from the front and push from the back for the quadruped, actually you can see it even better here, you'll get a little bit of forward locomotion. It's not great, but it's a good starting point. Evolution, if you created such a rudimentary neural network, you can actually figure out the synaptic weights for that. You could start evolution off with that, and it could see if it could improve the controller from that point. However, all of these three approaches have significant drawbacks, which is human effort. So what we're going to talk about today is the Resilient Machines Project. It was originally known as the EEA, but not as sexy a title, so it was eventually replaced with the Resilient Machines Project. Why was it originally called the Estimation Exploration Algorithm? Because I'm going to show you that the Resilient Machines Project is made up of two separate evolutionary algorithms. The first evolutionary algorithm estimates the robot's current situation. Am I missing a leg? Have I stuck my leg into a bunch of mud and my leg is now heavier than it was before? We're going to run an evolutionary algorithm where the robot tries to estimate or evolve an accurate simulation of its current experience or its current state. It's then going to run a second evolutionary algorithm, which is much more like the one that you have, which is take the evolved simulator that contains a simulation of the damaged robot and evolve a useful controller for it. So the first evolutionary algorithm is going to evolve simulations. You can think of this as the body.urdf file. Evolution is going to alter the body, the simulation of the body of the robot, the simulated body of the robot, to more closely match the physical body of the robot. So we're evolving populations of simulators in the first evolutionary algorithm. In the second evolutionary algorithm, we're evolving neural network controllers in the evolved simulator. Okay, it's a summary of this project. Again, I'm going to dive down into the details. Okay, so we're not going to have time to finish this today. We have 7 minutes left, but I'm at least going to start us off here. I'm going to walk you through a run of the Resilient Machines project from start to finish. We start with our physical robot. This was a project carried out for NASA. We're going to assume that NASA says this is the rover, this is how it's built. So we built our own quadruped to test things out here on Earth to see how this would work. We're going to make an odd assumption. We're going to assume that even though we have the physical robot, we're not going to tell the physical robot how it's put together. We're only going to tell the physical robot that it's made up initially out of 9 parts. Remember, start counting from 0 in computer science. We're telling it a little bit about how these parts, we're going to tell it a little bit about these parts. We're going to tell it about the size and shape and mass of these 9 different parts. The little gray blocks here correspond to motors. So we're telling it that 8 of the 9 pieces have motors associated with them. So we're going to tell the physical robot the pieces that it's made from. But the robot is going to have to evolve or estimate a description of itself. It's going to have to evolve. It's going to have to evolve an aggregation, a way of, or sorry, it's going to evolve a combination, evolve ways of putting these pieces together. Okay. Before the robot starts evolving a description of self, it's not going to be able to tell which way of putting these pieces together is correct because the robot doesn't know anything about itself. This robot has no camera. It can't see itself. The only sensors that this robot has is 2 tilt sensors. And these are usually known as vestibular sensors. I think we mentioned vestibular sensors already in this class. You have 2 vestibular sensors. Where are they? Where are they in your body? Vestibular sensors are tilt sensors. They're in your inner ear. So you know how your head is oriented relative to gravity because of fluid sloshing around in your inner ear, which gives you a vestibular sense, the tilt of your head. This robot has 2 vestibular sensors. The first one tells the robot how much its torso is tilted left and right. The second vestibular sensor tells the robot how much its torso is tilted forward and back. So this robot, whenever it moves, gets 2 sensor values in return. When this robot, quote unquote, pushes against the world, when it moves, it only knows how the world pushes back through these 2 numbers. So this robot, first of all, not only does it not know how to walk, it doesn't even know how it's put together. For all this robot knows, it's a snake robot, that this object is attached to this object. Object 2 is attached to object 1. Object 3 is attached to object 2. 4 to 3, 5 to 4, 6 to 5, 7 to 6, 8 to 7. Could be a snake robot, could be anything else. It doesn't know. We're trying to limit the amount of information we tell the robot about itself because we want to test how well this robot is able to evolve or estimate or figure out on its own a description of self. Okay, so before it can start doing that, the robot has to get some information. So the robot is going to perform a random action in a moment and observe the sensory repercussion. Okay. I think the arrows, the arrows get covered up here. So the robot knows that it has 8 motors. It knows that these motors have numbers, 1, 2, 3, 4, 5, 6, 7, 8. So the robot knows that it can send desired angles to one or more of these 8 motors, but it doesn't know where on its body these motors are. Imagine that you were trapped inside of a black box and there were 8 levers placed in front of you. If you pulled on one of these levers, you would feel the black box tilt some amount left and right and tilt some amount forward and back. If you pull another lever, you feel the black box tilt in some other way. That's the proximal view of the robot. That's how I want you to put yourself in the robot's shoes. If you did this for a while, I'm pulling on these levers, and then I asked you, and then I told you that there were 8 of these parts attached to the black box. I wanted you to tell me how these parts were attached to the black box based on your pulling of the lever and sensing vestibular repercussions. That's the task that the robot is pulling out. That's the task that the robot is trying to pull off. It's clearly a difficult task. If you try and imagine yourself trying to do this, it's very difficult. And it's non-intuitive, which, as usual, suggested to us that this would be a good task to turn over to an evolutionary algorithm. In this example here, the robot starts by moving at random. The robot sends 2 negative numbers to motor 1 and motor 5, which are here. Motor 1 is here. Motor 2 is the second shoulder. Motor 3 is the third shoulder. Motor 4 is the fourth shoulder. 1, 2, 3, 4. Motor 5, 6, 7, 8 are the 4 elbows. Again, very similar, I think, to what you have in the quadruped experiment. So in this case, the robot sent 2 negative numbers to motors 1 and 5, and it sent positive numbers to the other 6 motors. This is what happened. Negative numbers correspond to the motor rotating its part downward. Positive numbers correspond to that motor causing its part to rotate upward. If you were in the black box and you pulled levers 1 and 5 and you felt the black box tilt to the right, what could you conclude about the physical objects to which motors 1 and 5 are attached? Sorry, you may need a little bit more information. If you pull levers 1 and 5 down, you know that whatever objects are associated with those levers are going to rotate downward. You pull levers 1 and 5 down and you tilt to the right. What does that tell you about the location of objects 1 and 5 relative to your black box? I see we're out of time, so I will leave that with you as food for thought. You have a quiz due tonight. Logan has correctly diagnosed. You would know that those objects are at least to your left. You have a quiz due tonight. Please read through the entirety of the final project Google Doc and the Reddit page. Please ping me if you have any questions. Come see me in office hours. I'm happy to provide some clarification on the final project when we're all back here Thursday morning. Otherwise, have a good rest of your day, and we'll see you then. Thanks, everyone. Bye-bye.
We have class on Thursday.